Today, we are tackling a massive question. What is the universe actually made of? And I don't just mean the big stuff, stars and planets. I mean everything. You, me, the air we're breathing right now. The answer to all of that? Well, it lies in the fundamental rules of chemistry. And that is exactly what we are going to unpack together. Seriously, just take a second to think about that. The screen you're staring at, the coffee in your mug, even you. What is all this stuff at its most basic, fundamental level? Well, chemistry is the science that actually gives us the answer. You can think of it as the ultimate instruction manual for everything, for all the stuff in the entire universe. All right, so here's our game plan. We're going to start by breaking down how chemists sort everything in existence. Then we'll get into the language they use to describe it all. After that, we'll look at the rules they follow to make new discoveries. And finally, we'll check out their ultimate cheat sheet for organizing it all. Okay, first things first. Let's get organized. You see, before you can really understand matter, you have to know how to sort it. And chemists? Well, they have a really logical system for doing exactly that. The very first big split a chemist makes is to divide everything into two main buckets. In one bucket, you've got pure substances. These are things made of only one type of particle. Think of a pure gold bar or a glass of totally pure distilled water. And in the other bucket, you've got mixtures. The air we're breathing is a perfect example. It's mostly nitrogen and oxygen gas, right? But they aren't actually bonded together. They're just kind of like roommates sharing the same space. So let's zoom in a little on those pure substances. The most fundamental of all of them are the elements. I want you to think of them as the universe's primary Lego bricks. You simply cannot break down an element, like pure oxygen or copper, into anything simpler using a chemical reaction. That's it. They are the foundation. Now, what happens when you start snapping those Lego bricks together? You get a compound. And this is the really cool part. When elements bond, they create something totally, completely new. Get this. Sodium is a metal so reactive it literally explodes if it touches water. Chlorine is a poisonous gas. But when you chemically bond them together, they form sodium chloride, which is just regular old table salt. I mean, how cool is that? That's the amazing transformative power of a chemical bond. And this diagram here shows that difference perfectly. Just look at the top row, the one labeled A. See how those two different types of particles are actually snapping together to form brand new pairs? Their basic identity has changed. That is a chemical change. Okay, now look down at row D. See? The particles are just jumbled up in the same container. They're hanging out, sure, but they haven't bonded or changed who they are. That's a physical change. All right, let's try to apply this stuff. Let's say you have a mixture of alcohol and water. They're all mixed up, but they aren't actually chemically bonded. So how would you go about separating them back into pure substances? Well, the answer is a process called distillation. See, alcohol boils at a lower temperature than water, so you can just heat the mixture, capture the alcohol vapor as it boils off first, and then cool that vapor back down into pure liquid alcohol. And it's a totally physical process because you never actually changed what the water or the alcohol were. So now we know how to sort matter, but how do we, describe it? That brings us to our next section, the language of chemistry, which is all about properties. You can think of these as the adjectives of the entire material world. And just like we did with matter, we sort properties into two main categories. You've got physical properties. These are things you can observe or measure without actually changing the substance itself. We're talking about its color, its density, its melting point. Then you have chemical properties, which describe its potential to change into something brand new, like whether it's flammable or if it'll react with an acid. And here is a fantastic example of a physical property in action. The metal gallium. Its melting point is around 30 degrees Celsius, which is just a little bit warmer than room temperature. This means it can literally melt right in your hand. The fact that it can melt is its physical property. The act of it actually melting, that's a physical change. It's still gallium, just, in a different state. And here's another really cool physical property, ductility. It's a fancy word chemists use to describe how well a material, usually a metal like copper, can be stretched out into a really thin wire without breaking. It's an absolutely essential property for making all of our electronics work. And on the flip side, we have a classic chemical property, combustibility. This isn't about what something looks like. It's about what it does when you have air and a flame. Its ability to burn and completely transform into ash and smoke and gas, that's a fundamental chemical property. Okay, so we can sort matter and we can describe it. But how do we actually discover new things about it? Well, that brings us to the chemist's rulebook,
the process for asking questions, and, just as important, the non-negotiable symbols for doing it all safely.
You know, at the heart of all this is the scientific method. Yeah, you probably learned it back in grade school, but do not underestimate it. The structured way of thinking is the powerful engine behind every single chemical discovery. It's this formal process that takes us from just a simple question all the way to a conclusion that's backed up by real, hard evidence. Let's see it in action. Here's some data from an actual experiment where students were testing how the intensity of light affects photosynthesis in a plant. What they did was they changed the distance of a lamp and then measured the amount of oxygen the plant produced. This is a perfect real-world application of the scientific method. So, take a look at that data. What was the one thing the students were intentionally changing to see what effect it had? Or, to put it in scientific terms, what was the independent variable here? If you said the distance of the light source, you are exactly right. That is the independent variable. It's the one thing the scientist changes on purpose. The dependent variable is what they measure to see the effect. In this case, that's the volume of oxygen, because the amount of oxygen the plant makes depends on how far away the light is. See how that works? Of course, you can't really do experiments without knowing the rules of safety. So let's do a quick-fire round on some universal safety symbols you'll see in a lab. First up, the classic skull and crossbones. This one is unmistakable. It means a substance is poisonous and can cause immediate, serious harm, or even worse. When you see this symbol, you take extreme care, no exceptions. Next up is this one here. You can see it's damaging both a hand and a piece of metal. This is the symbol for corrosive material. It's a huge warning sign that the substance can literally burn or eat away at your skin, your eyes, and even solid metal. Okay, here we are, the final section. We've talked about what matter is, how to describe it, and the rules for studying it. Now, let's look at the single most important document in all of chemistry, the periodic table. And trust me, it's not just some chart to memorize, it is a map to all the elements. You know, the most basic division on this whole map is between the metals, which fill up the left and center, and the nonmetals over on the right. And they're basically opposites. Metals, they tend to be shiny, you can bend them and stretch them, and they are great at conducting heat and electricity. Nonmetals, on the other hand, like the carbon and oxygen that make up so much of our bodies, are usually dull, brittle when they're solid, and they're really poor conductors. And that pretty much brings our guide to a close. Every single element we have ever discovered, from the hydrogen in the most distant stars to the heavy elements we can only create in the lab, has a home right here on this table. It's a living document. It's a map of everything we know. It is the ultimate proof that with just a few fundamental rules, we can actually begin to understand the entire universe. And the only question left is, what are we going to discover next?